So this first problem is picking up with what we were doing on Monday with mean value theorem. And so remember, for mean value theorem, the first thing we have to do is verify. That requires that our function must be continuous on our interval, and it must be differentiable on the interval. Now in this particular case, it's both continuous and differentiable. We know because it's just a polynomial function. Polynomial functions are both continuous and differentiable, all the way from negative infinity to infinity. So having now verified it, we're going to find the values of c. Now remember, mean value theorem says that at some point, the slope of this equation will equal the slope of that function between just the points 2 and 5. In other words, the endpoints. So we got to do two things then. In order to find that slope function, we find the derivative. So we should have found f prime of x, which in this case is hopefully fairly straightforward. It's going to be 6x minus 5. And we also need to find out what the slope is between our endpoints. So we're going to do f of 5 minus f of 2. Actually, let's go ahead and write it out the long way here first. F of 5 minus f of 2 over 5 minus 2. If you did it as f of 2 minus f of 5, that's fine, as long as you also did 2 minus 5 on the bottom, of course. All right, f of 5. So we got 51 minus f of 2. Okay, and then we do the 5 minus 2 on the bottom, so that's going to be a 3 there. So it's 51 minus 3, which is 48. 48 over 3 equals 16. So then, that's where I now go with my derivative function over here. I'm looking to see when does that derivative equal 16. And so we're just going to solve it now from here. So add the 5 to both sides, and then divide both sides by 6, and we should find that x, which is just our c value, is going to be 21 divided by 6, which would be 3.5. That is then our answer. So in other words, what this means is that when x is 3.5, it has the exact same slope as if I drew a straight line between those two endpoints of this function. Now we're going to look at a very different application of this one. So take a moment, read through, even write down this problem, and then think about how could we do it. All right, so in order to know that the acceleration at some point hits 120 miles per square hour, then basically we can still use mean value theorem. But it's because we actually know 120 is a particular number. If we can go through this and verify that this will be continuous and this differentiable, then we've met the requirements for mean value theorem. Mean value theorem lets us prove that the slope at some point reaches the same slope as between the endpoints, which if that is 120, that will then be enough. So first of all, can we conclude that this is continuous? Well, we don't have an actual equation, but can we still know that the relationship is continuous? Yeah, because f here is really a velocity function. And so is velocity then continuous? Yes, because as we're going along, there's never a point where the velocity does not exist. The car is always traveling at some speed, at some velocity as we're going along. Now, is it differentiable? This one we got to think a little bit more deeply. Remember, in order for something to not be differentiable, it means that we would have to hit, say, an asymptote. Could this hit an asymptote?
No.
No, because that means you're approaching infinity. If our velocity is approaching infinity, we have bigger problems. Or a hole in the graph. Again, if there was a hole in the graph, that would mean that at that point there was no velocity.
Wouldn't it not
And
be continuous
that can't be. Yeah, that would be another discontinuity then. But what about differentiable? What about a corner?
No.
Is it possible there could be a corner?
No, because
Well, let's say you're currently at a velocity of 30 miles an hour, can your velocity instantly become 50? No. It can't instantly become that. There's always a progression. No matter how fast that progression takes place, there's always some sort of progression, even if you hit a brick wall. So, because of that, we can then conclude that in this kind of a situation, there are no corners in the graph either. So, for that reason, we can conclude, yes, it is differentiable. All right, so then, all we need to prove now, in order to prove this statement, is to prove that the slope between A and B is 120. So, please do that. Please find out, what is the slope, or another way to think about slope in this context, the average velocity between A and B. Or average acceleration, actually. All right, so to find slope, it's like f of A minus f of B kind of stuff, right? Well, notice what our speed is at the start. Let's call it 30. We're calling 30 the start. Minus 50. I could do 50 minus 30 as well. I just would have to switch the order when I put it on the bottom as well. And so then that's time 0 minus the next time. Now this is the one little tricky bit here. What will this time be?
100.
How much time has passed? 10 minutes. But this is not going to be 10 here. Because notice our units here. It's miles per hour, or square hour. So we have to put that in hours. 10 minutes is how much of an hour?
1/6. Repeating.
1/6. So, do that calculation, please.
120.
And so we end up with negative 20 divided by a negative 1/6. The negatives, of course, will cancel each other out. And then dividing by 1/6 is the same as multiplying by 6. 20 times 6 is 120. We now verified that the slope between A and B is 120. That means that according to the mean value theorem, the acceleration of this car at some point has to have been 120 miles per hour squared, or 120 miles per hour of acceleration. Here you have a graph shown of f prime. Over what intervals on this graph is f increasing or decreasing? And I'm going to give you a little bit of time to think about it first. Just make sure you really think it through. Now, the part that does make this tricky is that the graph here, remember, is f prime. The graph we're looking at is the derivative, and it's asking when the original is increasing or decreasing. So, the original is increasing when the slope is positive. Remember, derivative just means slope. So that means that if we are above the x-axis, we are positive. Therefore, this would be increasing everywhere through there. So, you notice then it must be increasing between 0 and 1.
Wait.
And then it is also going to be increasing between 3 and 5. So, how do we write our actual intervals though? So, for increasing, I said that it's from 0 to 1. On the left side, should that be a parenthesis or a bracket?
Parentheses.
All right, so in this case, you'll notice that at 0, we have a closed dot. Now, if this was the original and we were trying to find the derivative of it, we wouldn't be able to find the derivative there. But remember that this graph does represent the derivative. So there is a derivative at 0, and so yes, we can include that. All right, now what about on the right side of this, after the 1? Should that be a parenthesis or bracket? Yep, that one is parenthesis. Because at 1, it's 0. And for increasing, we're looking to see where is it positive, basically. So that's what we're looking for. All right, now we're also going to be noting the decreasing part. I'll put that down here. And notice it's decreasing wherever our slope is negative. So that means throughout this, from 1 to 3, it's going to be negative. So it's decreasing from 1 to 3. Notice the parentheses, not brackets, because again it equals 0 at the ends. All right, next up, union. And then you go from 3 to 5. Both of those are parentheses. And then for decreasing, we go back negative down here. And so that is a union again from 5 up to 6. And should the 6 now? Bracket or parentheses?
Bracket, Buster.
Bracket. Because notice that point is a full circle. We do know what the derivative is there, so we know the derivative, yes, is negative, so it is included. Now, having gone through that then, let's formalize this. This is how we can check if a function is increasing or decreasing based on the derivative specifically. So please add this into your notes. All right, so back to the same graph again. Now to keep going with some of these ideas, this graph still represents the graph of the derivative, and we're still answering questions about the original. Take a moment and think through, based on this graph, when does the original function have a local maximum or a local minimum? All right, now this one can be a little bit tricky, so I want to kind of bring it back to the original function. So I'm going to just kind of make a rough sketch of the original function as we're going here. So right here, notice we have a positive slope. So I'm just going to go and show some place there where that means the graph is increasing there. Here, our slope is 0, meaning at that point it's flattened out. Now let's put that a little bit higher. We're going to have some room to work. All right, so we know it flattened out up there. Down here, notice our slope is negative. And that's really all that's telling me, is that it's a very negative slope there. So there we have a negative slope. Here, our slope is back to 0. Here, our slope is positive. Here, our slope is back to 0. And you're going to be seeing problems like this that you have to do on your own as well. And this is a nice way to kind of start these out, is grab some points along the way and think about, is the slope positive, negative, or 0 kind of a thing. And notice based on this, I can kind of get a rough idea about what it's doing. And I can kind of sketch in maybe some curves. I'm not saying that this curve is the exact same as the one that would create that derivative graph, but it's a nice idea of kind of a rough sketch. Help if I target it out better. And it then can help us look at for the maximum and minimum. So where do we see local maximums occurring?
There and there. 0.
We got a local max here at 1. And we have a local max happening up here at 5. Okay, what about local minimums? Where do we have a local minimum?
3.
3. Okay, we got a local minimum here. Do we have a local minimum here? No. Remember that for the local minimum or maximum, it has to be that minimum or maximum from both sides. When we hit endpoints like this, we can't necessarily make that conclusion. And because we're only given this part of the graph, that's as much as we can say on it. So the big question here, though, is what must be true about the derivative function in order to be able to tell just from that, without having to make the original graph, that we are at a local maximum or a local minimum?
Where is the local maximum?
Excellent, yeah. One thing to look for, and notice here, is that, notice each of these cases is where we actually hit 0. But how can you tell which one's going to be which?
I know.
Yeah. So notice when we change from positive to negative slope, we are at a maximum. And you can kind of see why that is if we think about the graph here for a moment. Because what that means is that our slope was positive and then our slope become negative. So we were heading uphill, but then it changed to we're heading downhill. So we have to have reached the maximum there. And similarly, the minimum means we're changing from negative and heading into positive. So with that in mind, again, we need to formalize some notes here. This is called the first derivative test. Yes, tomorrow we will be getting into the second derivative test. All right, so now some specific examples from the first derivative test here. So you'll notice here how we end up with like a local maximum. The local maximum can occur when we change from positive to negative slope, because you notice it's increasing, and then it stops increasing and starts decreasing. Therefore, maximum. Local minimum, same kind of a thing where it's decreasing and then it starts increasing, hence why it's the minimum. But you'll notice this third option talks about one that we hadn't seen before. If the sign does not change at the point, then it is not a maximum or minimum. So we can see that in these last two down here, where if the slope is positive and then it's positive, you notice the sign didn't change. Even though it did equal 0 here in the middle, it didn't change. So it flattens out. We'll actually talk about this as a point of inflection at some point. But it's not a local maximum or a local minimum there. Same kind of thing when it goes negative to negative like that last one there. All right, so for doing this problem now, notice we're asked when is it increasing or decreasing. So to know it's increasing or decreasing, then we have to know when is the derivative positive and negative, because that was our increasing and decreasing test, the first set of notes that we took today. So step 1, find the derivative of this function. And then once we find the derivative, we now need to figure out where does it equal 0, because of course it's going to change from positive to negative by going through 0, or from negative to positive by going through 0. So now set this equal to 0 and solve it. Yes, it is factorable, so factor it. So we go factor it. Now, yes, you could go ahead and do like the grouping method or the airplane method, whatever is your favorite for doing this one, but factoring that one's fairly straightforward, because we know that in order to get a 2x, you got to do 2x and x. In order to get a 1, we know it's 1 and 1. Basically, it's just a matter of what sign is what. And if we're going to add to a positive x, I want more positives than negatives. So I want the 2 to multiply by the positive. Having done that, we now know what x equals. X is going to equal a positive 1/2 and a negative 1. Those are my dividing lines when it comes to my intervals, because that's where it's 0. So I now have 3 intervals that I need to go through and I need to be checking here. So I have from negative infinity up to negative 1. And notice we aren't given a separate interval that it's over, so that's why I'm going all the way out to infinity here. I need to be checking negative 1 up to 1/2. And I need to be checking from 1/2 up to a positive infinity. And basically all we need to know is within each of those intervals, is it positive, negative, or 0? Now, what am I checking to see, though, if it's positive, negative, or 0? Remember, I'm checking to see if it's increasing or decreasing. Increasing is when the derivative is positive. Decreasing is when the derivative is negative. So you're actually plugging into the derivative function in order to figure that out. Now, a little tip with these, you can plug it in, of course, to any of these different equations that we wrote, any of the different forms. I actually find it a little bit easier plugging it in here, because oftentimes you can plug in a number and tell very quickly if it's positive, negative, or 0. For instance, if I plugged in, I'm going to plug in something out of here. I'm going to plug in a big negative number. And that's as specific as I'm going to be. I'm plugging in a big negative number. 2 times a big negative number minus 1. Will that be positive or negative? Negative. A big negative number plus 1. Will that be positive or negative?
Big negative number.
And what's a negative times a negative?
Positive.
So then, this slope is positive through here.
So,
Now, you can use any of the equations, but that's a nice little trick to be able to do it. Now, with this one, though, you're probably going to have to be a little bit more specific.
0.
But, of course, 0 is a nice, easy one to use there, right?
Oh, 0.
So, plug 0 in. Honestly, with that one, it might be easier to plug it into the first one. But choose the one that's easiest there. So, having done that, you notice that we have a positive, a negative, and a positive. That's where the slope is positive, negative, and positive. Remember, wherever it is positive, that means that the function is increasing there. And so when I write where it is increasing, I'm going to write it as negative infinity to negative 1, union with the 1/2 and the infinity. I chose to write the 1/2 as 0.5 here, not because one is better than the other, but because 1/2 is a pain to type in this particular program. All right, and then it's decreasing just from negative 1 to 0.5. Again, we're going with parentheses, not brackets here, because at the actual endpoints, it's 0. It's not increasing or decreasing there. All right, now having done that, we now are going to go on to the second part of the notes we took today. We are going to find out where is the local maximum and minimum values of our function. So before we do it together, take a few moments here. Think about how would you answer that. So remember from your notes, we saw that when f prime, that is our derivative function, which is what this stuff represents, changed from positive to negative, we are at a local maximum. So to find my local maximum, I'm looking to see when did it go from positive slope to negative slope. Well, it looks to me like that happens at negative 1. And then where does it go for the local minimum? In other words, where does it change from decreasing to increasing? At 0.5. I'll write it as 0.5 here just for consistency, but again, 1/2 is fine. Now, a little detail here. Notice these two numbers I put down for the local max and local min. Those are what? What would those actually represent? What variable are those? Those are actually my x values. And so I'm not going to worry about doing it right now, but depending on the type of problem that you're being asked to do, since we're asked for the local maximum and minimum values here, if it just was worrying about the x value, that would be my answer. But sometimes we're actually going to need to give the coordinates of the point. And so then we'd have to plug that number back into the original function, back into f, not the derivative, to figure out what that answer is. So then, with that knowledge, please go ahead and repeat that basic process for this one. Please find the intervals where this one is increasing and decreasing, and then also find the maximum and minimum values of the function. So for the first part, just deciding where it's increasing and decreasing, here's all your work and everything that goes through. Notice it does not switch signs here, and so both of those are decreasing. You still have to put the union with them though. We can't just say negative infinity to 3 because remember we have to exclude 0, because at 0 it's not decreasing. At 0 it is horizontal. Our slope is 0 there. Once you have that, use it to find the local maximum and minimum values. Now, when it comes to doing the local max and min in this case, remember I'm looking to see where it switches from positive to negative or negative to positive. But in this case, that only happens once. It only happens here. Now, notice what number that happens across. The one shared between those two is the 3. So at 3, so at x equals 3, we are changing from negative to positive. Does that mean that it is a local min or a local max? Yep, that's a local minimum because it's going from a negative slope to a positive slope. We're bottoming out there. So yes, that is a local minimum. Good. And is there a local maximum though? No, because it never changes from positive to negative. So what happens at 0? Neither. That's not a local minimum or a local maximum.